Okay, so let's start. So just some reminders. Homework 3, you all know, due on Thursday. I see that there's a lot of activity on Piazza, so many of the questions, I think we kind of answer them if you really read the write-up carefully, but still okay, especially if you can answer your friends' questions. I think it helps everyone. Remember that the project proposals are due in 10 days. We're going to give you some submission instructions. I think we're aiming at trying to get some, in addition to my reviewing of the proposal, also some peer review, so you will be able to know what other project people are working on and comment on it if you have interesting things to say. Questions? Comments, suggestions? Okay, so let's move on. So we are talking about learning theory, and this is kind of where we left off. So what did we do last time? We defined PEC learning. We gave a definition. I point you here. It's slide 24, a few slides back. We know what does it mean to be PEC learnable. We proved in what we called an Occam's razor result, something that shows what's the dependence of learnability in some complexity parameter, epsilon, delta, n, and how many examples do you need to see and be consistent with so that you can guarantee that with high probability you're going to make a little bit error in the future. And this really led us to the important thing. We concluded with a consistent learning scheme, which really is written here. So immediately from our definition and the Occam's razor result, really this is what we got. So the basic thing is that we take a sample. If we manage to find a hypothesis that is consistent with all the M examples, and M is not large enough, this is the M that we want. So if we take this size sample, something that is proportional to 1 over epsilon, the accuracy we care about, 1 over delta, the confidence within which we want to make sure that things are okay, and the log of the size of the hypothesis class, if this is M, then everything is going to be okay. We show that if we manage to be consistent with these many examples, our behavior is going to be acceptable in the future. Okay? So that's why I call this a consistent hypothesis scheme, because essentially it gave us kind of a scheme for how to learn. Right? Take examples from the distribution, develop an algorithm that is consistent with this sample, and modulo these things, you're happy. Everything is going to be good. Now, you had 2 complaints about this, and we're going to address both of them today. One of them is this with word consistent. You said, you know, if I'm not exactly consistent for some reason, I'm almost consistent, what's going to happen? We're going to address this. And the second thing is that you observe that when I write this lan, the size of h is finite. Otherwise, I don't know what size of h. And we're going to address this most of today. So before, let's just play a little bit with this definition and get some examples. So this is really where we ended up last time. So we talked about the case of conjunctions. And we basically ran the theorem on conjunctions. And we said, well, for conjunction, our M is going to be something that is linear in n. And we're happy. In terms of sample complexity. Now we have to say, do we have an algorithm that does it? And we do have an algorithm because we actually showed last time that we have an algorithm for conjunctions that can be consistent with any number of examples you give me. And then we move to KCNF, a lot more expressive class of functions. And we said, if the functions that you're playing with come from this family, from a sample complexity perspective, it's also okay. We did some counting here, and we got to the fact that the log of this function space is n to the k. K is fixed, polynomial. We're happy. So from a sample complexity perspective, we're happy. And then the question is algorithm. Can we find an algorithm? And the observation we've made, this was the last slide of the last lecture, was that really what we need is to transform the feature space. Once we transform the feature space and replace our original space of literals with a space of disjunctions of size k, everything is going to be fine, because now we just learn a conjunction over this new space. Everyone is clear about this? This is really a basic step that we always do in learning, sometimes explicitly, sometimes implicitly, but we always do this. And I gave this example, and one important observation that we made at the end was that the notion of distribution is really important here. And this is one reason why it's important that PEC learnability is has a distribution-free assumption as a core component. Because when we do these transformations, the distribution that we start with the original feature space, is different than the distribution that the learner actually sees, because we transform the space. For example, I commented that this distribution will never be a uniform distribution. So if somehow you took your PEC definition and you said, instead for all distribution, I'm going to develop a theory that only learns over uniform distributions, we cannot do this transformation. It could be, of some significance that you can learn things over uniform distributions, and you'll find papers that do that, but you are going to lose some things, and this is one of the things you're going to lose, the freedom to transform feature spaces. And you'll see in about a week that you're losing other things. Powerful algorithms like boosting really rely on this distribution-free assumption. Okay, so now we have this example. Question on this example? We can move on and play with exactly the same thing with a few more examples. And I'm going to just run through a few examples and stop on one that is really important, and we'll see why. So the first example that we can think about is, okay, what about unbiased learning? That is, all Boolean functions are in my space. What happens there? So we talked about the beginning of the semester, and we all agreed that there are 2 to the 2 to the n different functions. You can remind yourself why this is the case. And therefore, the log of this is going to be exponential in n, which means sample complexity arguments show that this is not going to be PEC learnable. So at least we have one negative result so far. But we can think about many other relatively expressive function classes for which it's going to be okay. We talked about KCNF, and I'm giving here a few other definitions of classes of Boolean functions. The definitions are here. K-close CNF, KDNF, complete analogous to KCNF, right? It's a disjunction of any number of terms where each conjunctive term, each monomial, has at most k literals. And I'm going to stop on this class of function, k-term DNF, which is a disjunction, it's a DNF, of up to k conjunctive terms. This is why it's k-term. So again, this is a list. I did some counting here. You can think about how to count how many functions are in each of these classes yourself. The key thing that I want to discuss here is this specific class. In terms of sample complexity, everything is fine. Because if you count it, you'll see that just like KDNF, KCNF that we talked about, the size is going to be polynomial. Log of size of h is going to be polynomial. However, it turns out that even if you want to learn just 2-term DNF, so this function with two terms, just T1 or T2. So remember, T1 is a conjunction of any number of literals. T2 is a conjunction of any number of literals. And two-term DNF actually turns out to be problematic. So even though from a sample complexity everything is fine, from a computational complexity it's not the case. What does it mean? It means that we don't know how to develop an efficient algorithm. That you give me data, you tell me this data is actually consistent with a two-term DNF. Find a hypothesis. The same exercise that you did for conjunctions, sorry, and that we did for KCNF. This problem is NP-hard. Seems simple because the space is small, but it's NP-hard. So determining whether there's a two-term DNF consistent with a set of training data is NP-hard. And therefore, I cannot use K-term DNF as my H. But we've seen learning algorithms. So first of all, what you see here is it's spec-learnable from the sample complexity perspective, but it's not efficiently spec-learnable. What should we do? What we're going to do is we're going to change the hypothesis class. We're going to move to a larger hypothesis class. For KCNF, we know that we can learn KCNF. I'm going to argue now that KCNF is a superset of K-term DNF. That is, every function that is in K-term DNF can also be written as a KCNF. Again, this is a simple exercise that you can think about yourself. I'm going to give you an idea of why this is true. How would you go about proving something like this? Here's an example. In fact, the example here that I give is three-term DNF. And I want to argue that it can also always be written as a KCNF. This is a KCNF. This is a conjunction. Product is a conjunction. And these are disjunction of size 3, right? Three-term, 3 CNF. So how would you go about proving this claim? Idea? What does it mean the two functions are the same? Simple question. What does it mean the two functions are the same? Yeah? For every input, they have the same output. So let's take an input that we know, say, is a positive here, positive example here. We have to show that it's positive here too. Same thing. We'll take an input that is negative here, a negative example, and we'll show that it's negative here. If we can do this, we prove that they're equal. Okay, everyone agree about the methodology? Okay, so let's take a positive example of this function. And remember, I constructed a very specific KCNF here. How did I construct the KCNF? I looked at this function. This function is basically a disjunction of conjunctions, right? Each one of them is a conjunction. How did I construct my KCNF? Each disjunct here, each clause, I'm taking one literal from T1, another from T2, another from T3, and I'm taking all combinations. Okay? So now, what does it mean that I have a positive example of this guy? It means that it satisfies one of either T1 or T2 or T3, maybe all. Let's assume it satisfies T1. T1 in itself is a conjunction. So if it satisfies T1, what does it mean? It satisfies all the literals in T1. Now, each disjunction here has someone from T1, right? And therefore, all disjunctions here are going to be satisfied because they have someone from T1 and it's satisfied. And therefore, the conjunction of this is going to be satisfied. We proved one direction, right? We took a positive example from here. We showed it's positive here. Let's take a negative example. Once we take a negative example and show the same thing, we're done. So let's take a negative example here. What does it mean that it's negative for this? It's negative for T1, it's negative for T2, it's negative for T3. What does it mean that it's negative for T1, for example? At least one of the literals from T1 is off. Same thing here. At least one of the literals for T2 is off. At least one of the literals from T3. Let's call these guys X prime, Y prime, Z prime, respectively. Now, XY, Y, X prime, Y prime, Z prime is one of the clauses here, right? Because I chose all clauses, one from here, one from here, one from here. This guy is going to be negative. I don't know about the rest. I don't care about the rest. But at least one of these disjunctions is negative, and therefore the conjunction of all of them is negative. It's a negative example. Okay? So I prove very simple game with Boolean functions that every k-term DNF could be represented as a KCNF, and therefore, that's what I'm going to do now. You tell me that you have a sample that you've taken from k-term DNF, and you want to learn it. I'm going to suggest don't learn it using k-term DNF. Instead, learn it using KCNF. There is a function in the KCNF space that is consistent with this data, and we already showed yesterday, last time, that we can find it efficiently. So this is just an illustration of what we said here. So this is what we did, right? So we started with a class of functions, and there was a target function somewhere here. But the theorem says, well, it's actually hard to find. This theorem that this class is not efficiently learnable, by the way, was proven almost 20 years ago now by Lenny Pitt, professor here that you all know. What we are doing instead is we say, you know what, let's move to a larger class of functions and learn there. That's going to be okay. Because combinatorially, it's easier to search in a much larger space, and we can find it. So that's what we done. So this is really an important example of the importance of representation, right? So concept that cannot be learned using one representation can be learned using another, more expressive representation. This is the second example we see of that. We already saw an example where we talked about conjunctions, and we said sometimes it's hard to learn conjunctions, even though the data is consistent with some conjunction. Instead, we're going to move to linear threshold functions, right? We had exactly the same result, so it's really analogous to this. Okay, so this is, by the way, one powerful thing that once you have a theory, a concrete definition, and you can prove some theorems on it, you can analyze concretely what's good, what's bad, what can be learned, what cannot be learned. So, and I'm not going to talk a lot about this, but just want to say that, you know, the fact that we have this theory allows us also to prove negative results. There are things that cannot be learned or cannot be learned efficiently. For example, from a complexity theoretic perspective, we can prove things cannot be learned efficiently. We just cited a result like this. And from an information theoretic perspective, we can say, in order to learn this class of functions, you need too much data. It's going to be exponential in the complexity parameters. Examples. From a complexity theoretic perspective, we just talked about k-term DNF. It turns out the neural networks with a hidden layer, even if it's very small, in fact, even if it has one hidden layer, it's NP hard to learn. Starting on Thursday, you're going to learn, the next 2 lectures are going to be about neural networks. So, of course, we are learning neural networks. We have algorithms to learn it. But being consistent with a neural network is NP hard. And there are a few other interesting classes of functions that it's NP hard to learn. Read once Boolean formulas, for example. Read once means that every variable in the Boolean formula, or Boolean circuit, if you want, appears only once. This is actually an interesting class of function because it's related also to Bayesian networks that we're going to talk about a little bit later in the semester. And you can also prove things from an information theoretic, sample complexity perspective. DNF formula, CNF formula that are universal representation, all Boolean functions can be represented this way, cannot be learned. And there are some other interesting classes like deterministic finite automata or equivalently context-free grammars that cannot be learned using the kind of protocol that we are talking about now, provably. Okay, so I'm not going to give details on this. I want to move to address the 2 points that you asked me about last time. One is, what if I cannot be consistent? Right? So far, everything we did is with consistent learners. And basically, the answer is we prove everything for consistent learners because it's easy to prove. We proved an Occam's razor result in 5 minutes. Everything that we said about consistent learners actually transfers to the more general case. What is the more general case? I'm going to call it here agnostic learner. So the assumption is that we're trying to learn a concept using hypothesis F, using hypothesis in H, but F is not in H. I don't know where F is, in fact. Could be in a small class, you know, could be that there isn't an F, right? It doesn't matter. F is just expressed by the distribution. But the basic thing is that you have no chance of being consistent with the labeled data. So in this case, our goal should be to find the best possible. The hypothesis that minimizes the training error. So this is my training error, right? 1 over m, the number of mistakes I made. And I want still to get some guarantee, even though I did not manage to get 0 error on my sample, my training sample. I want to have some guarantee that in the future I'm going to be okay. So what kind of guarantee can we get? What would you like to get? So before, on the training data, I got 0 error. And I proved that in the future, it's going to be less than epsilon, where epsilon is related in a nice way to the size of the sample and a few other things. Now I'm not going to go down to 0. What do you want to happen in the future? Future plans. What's the best you can hope for? Yeah?
You still want error to be less than some specific value to be dependent on the training error?
You want some error that depends on the training error. You cannot do better than the training error, right? But maybe you can say, okay, so this training error is the minimum I can do, but maybe I can do just this plus some epsilon, rather than what we had last time, 0 plus some epsilon. So that's what we want to do, right? So the true distribution, which is this, the probability of making a mistake over the distribution, you want it to be related somehow to this. And the tool we're going to use in order to do this is something that is called hefting bounds, very related to Chernoff bounds you might have heard about. And basically the idea is that these bounds allow us to characterize the deviation between the true probability of some event and the observed probability or the observed frequency over some sample. So imagine that I give you a coin and I tell you it's a fair coin. You're going to toss it 10 times, 1,000 times. You're going to get some heads and some tails. It's not going to be exactly a half, right? You're going to get some, 45% of the tosses are going to be head. So hefting bounds allow us to quantify the gap between what you observe and what's the true probability. And the way it does it is this way. It says the probability that P, the true probability, is bounded by more than epsilon from what you observe, goes down exponentially fast in epsilon and in M. It's important that it goes down exponentially fast. And that makes sense, right? You would expect that it would go down as a function of M, and of course as a function of epsilon. The question is how fast it's going to be. The answer, exponentially fast. So really, think about it as P is the underlying probability, the biased coin, and P hat is what you observe. And that's exactly what we're going to use here. So in our case, P is going to be the true probability of the hypothesis. I don't know what it is, because I only saw my hypothesis behaving on my training data. But there is some true probability, right? True error of this hypothesis. If I had a chance to look at all the data, I would know what it is. And there is the observed error that is going to be our P hat. And I'm going to use this in order to quantify this difference. So this is what we're going to say. Just replacing the P and the P hat, the probability that the true error is epsilon away from the observed error is going to go down exponentially fast in M and epsilon. And just like we did before, I want this to be smaller than delta. And once I fix my delta, I'm going to isolate M from here, using exactly the same trick that we did last time. And that's what I'm going to get. I'm going to get, one way of writing it is, the true error is bounded away, is less than the observed error, the training error, plus something. And again, this something is inversely proportional to M. You should expect this, right? The larger the M is, the smaller the gap is going to be between the observed error and the true error. Make sense? And it's going to grow as a function of the size of the hypothesis class, just like we had before, and inversely proportional with delta. And of course, I can write this also. So this is where I'm writing it here as the gap between the observed error and the true error. And I can also take M, write it as a function of M, and basically I'm going to get that an agnostic learner, which makes no commitments to what's the target function, and returns the hypothesis with the least training error over at least these many examples, is going to be guaranteed that with probability at least 1 minus delta, its training error is not going to be off by more than epsilon from the true error. And this M, I just reversed the formula from this slide. So M is greater than something that is inversely proportional to epsilon, inversely proportional to delta, and proportional to the log of h. Okay? The only difference, if you really look at the details between this and the previous one, is that here we have epsilon squared. Before we had epsilon. This is kind of the tax we pay because now it's agnostic learning. And technically, one can prove today bounds that are a little bit better, but conceptually they are about the same. So the dependence on epsilon is about the same. Some constants could change. This is the bottom line, right? The bottom line is that learnability really depends on the size of the hypothesis space. If this is polynomial, we can learn. If it's not, we cannot learn. Modulo complexity, of course. The ability to compute efficiently the hypothesis. Questions? Okay. So we answered one part, right? We defined learning, and we talked about how to quantify the dependence between the number of examples we need to see, the error we're going to incur in the future, and the confidence within which we are sure that this is going to be the error we'll see in the future. M, epsilon, delta. Okay? Now we still have to deal with this problem that you identified before, and let's look at it this way. So now I want to learn the concept of axis parallel rectangles. So I have 2 dimensions, x, y, real valued, and my concept class is a rectangle. I know that, which means there's some value here and there's some value here, two values here and two values here, and if it's within this rectangle, it's a positive example. Outside the rectangle, it's a negative example. Okay? How would you learn this concept class? I'm going to give you positive, negative example. Give me an algorithm. Here's a positive example. What do you know now? It again? It's within the rectangle. So what is your hypothesis? What do you want to return at the end? What does it mean that it's a rectangle? Yeah.
If you should move either of the axes.
Okay, so you give me an algorithm, something about moving the axis, the x-axis and the y-axis, as a function of the examples I see. Before we do this, so tell me, what is going to be the output? Yeah?
X and Y, just a vertical line.
Y, only one x and y. I need to define a rectangle.
Because you know it's not about x equals 0 and y equals 0.
Oh, I don't. Okay.
Oh, you don't?
So let's assume I don't.
So
Four numbers, right? The maximum x, the maximum y, the minimum x, the minimum y. That's going to define the rectangles. And so I need to return 4 numbers. Now, how do I find them? Yeah?
I can learn for functions and look if all functions meet.
Right, so basically, here are 2 positive examples. What do you know now about the rectangles? What's your current hypothesis? You take the max of the x-axis of these 2 examples, the mean of the x-axis. Same thing for the y, and you know, this is my current hypothesis. I give you another example. It's negative, hasn't changed anything, say. Maybe you could change it, but you don't have to. Here are 2 positive examples. You're going to change it, right? So you're going to push this at least to this point and push this down at least to this point. You'll get something like this, and so on. So you can develop an algorithm, but can you prove to me that you've learned? Can you use any of the theory from a few minutes ago and last week to prove that you've learned? Right? So this is, so will we be able to learn? Is this class of function learnable? So you cannot say anything because there are infinitely many rectangles. So we can't even say that we can come close in any quantifiable way. So that's what we're going to do now, right? So I want to be able to replace the size of H, the size of the hypothesis class, with something that tolerates infinite spaces. So the intuition is that infinite hypothesis spaces also have some levels of expressiveness. For example, if I think about rectangles versus 17-side polygons, or just convex polygons, without limiting the number of sizes, these are 3 distinct classes of hypotheses, but one is more expressive than the other. Or linear threshold functions versus conjunctions of linear threshold function. Right? So linear threshold function separates the space, positive here, negative here. Conjunctions of, let's say, 2 is more expressive. Right? I have to satisfy both this linear threshold function and this linear threshold function. And so on. So that's what we want to do. We need a measure of expressive of an infinite hypothesis space, and the size is not going to do it because they are all infinite. So what we're going to develop in the next half an hour is a notion of VC dimension, Vapnik-Chervonenkis dimension, that will replace the size of H. And in fact, it will replace it in such a beautiful way that basically in each of the theorems that we quoted before, we can take size of H, replace it by VC dimension of H, it's about right. So all the dependencies that we've understood before are going to really transfer to this case. So the key notion in order to understand expressivity of classes of functions, or the type of expressivity that is important for learning theory, is this notion of a shattering. So I have a bunch of points, and when I have a bunch of points, and I'm thinking about a Boolean functions, there are many, many ways a Boolean function can label these. And the number of possible labelings that a given function or a given function class can deal with it, can label this, is going to be related to this expressivity. So let's start small. So here are 2 points. I have 2 points. How many different labelings do I have for 2 points? Just 2 points. How many possible labelings can I give to 2 points? 4. Both can be negative, both can be positive, 1 positive, 1 negative, and vice versa. Right? 4 options. Now, in all cases, I can put a linear function between them. I don't show all the examples here. I show just 2 examples. You know, this is positive, this is negative, this is negative, this is positive, and I can also put the green line here, and both will be negative or both will be positive. Right? So I can do it. So linear functions are expressive enough to shatter 2 points. But if I show you this set of points, if I label it this way, it's fine. You know, positive here, negative here, linear functions can do it. But if I label it this way, hopefully you can see the distinction between these 2 colors. Yeah, you can. Then linear function is not going to do it. I can try this way, this way, this way. It's not going to work. Right? Linear functions are not expressive enough for this specific labeling. But I can try a more expressive function. Yeah, this function actually does it, right? It puts positive on one side, negative in another. And that's really the idea, right? So the idea is that if you have a lot of options in labeling a given set of points, you need a more expressive set of functions. This is what we mean by shattering. So we're going to say that a set S of examples, a fixed set of examples S, is shattered by a set of functions if any partition of the examples into positive and negative examples can be expressed by a function in this class. Okay? The intuition is that if you have a large set of points, m points, there are 2 to the m possible ways to label it. You need a rich class of functions so that you can express all these 2 to the m labelings. So let's start with some examples. Here is a class of functions. This class of function is left-bounded intervals on the real axis. So 0, A. Between 0 and A is positive example. Outside 0A is negative example. So this is an infinitely large set of functions. Everyone agrees? How many points can I shatter? If I give you 1 point, you can shatter it, right? You want to make it positive. So let's say the point that I gave you is 2 on the real axis, x equal 2. If you want it to be positive, you'll choose A larger than 2. This is a class, a function in your class of functions. If you want it to be negative, you'll choose A to be a half. These are the only 2 options. You can shatter it. Here is a more, and this is basically what I'm doing. So if the example is here, you choose A to the right of it. Otherwise, you choose it to the left of it. So, but set of 2 points cannot be shattered. Why? Yes?
Because if I have the smaller one, once you have minus.
Right. Exactly. So if I give you 2 points, the labeling that assigns negative to the left one and positive to the right one, you cannot shatter it. You cannot express it with these kind of functions. Everyone agrees with that? Okay, let's move to a more expressive class of functions. So again, now I'm going to have intervals. So I have two parameters, a and b. Infinitely many functions, right? Because a and b could be any real numbers. And in this case, what about 2? 2 points. Can you shatter 2 points? Any of the 4 configuration of the 2 points, you'll be able to place an interval in the right place. If you want all of them positive, you'll place it around it. If you want them negative, you'll put it here, and so on. One positive, one negative, you can do whatever you want. So this is just a comment that will make sure that we understand that this is a set of functions, right? It's a set of functions that labels positively any numbers between a and b, and negatively any numbers outside. Okay, but what about 3 points? Can you shatter 3 points? Someone? No. Why not? Need help? So you will choose a specific labeling where you have 3 points. You'll choose the middle one to be negative and the other two positive, and this cannot be expressed using this set of functions. Okay, so, but all sets of 1 or 2 points can be shattered. Sets of 3 points cannot be shattered. Let's move to a more interesting example. Linear threshold functions. We're going to keep it in the plane. So I call it half spaces in the plane. So it looks like this. So my claim is that sets of 1, 2, or 3 points can be shattered. Sets of 1 points, think about it. Of course, you can put the half space wherever you want. 2 points, 3 points. Can you always shatter a set of 3 points? Always? Give me an example of a set that you cannot shatter. Yeah.
Points are on a line, and it's like positive, negative, positive.
Yeah. So if I give you a set of 3 points and they're on a line, there is a labeling that you cannot express. Put negative in the middle, positive outside. But there are sets of 3 that you can shatter. Just put any in a general position, not on the same line, then you can shatter it. Agreed? So not all sets of 3 can be shattered, but some sets of 3 can be shattered. That's an important distinction, remember. What about 4? I claim that no set of 4 points can be shattered. Why? Any suggestion for an argument? XOR is the right intuition. How do you say it? Here is one way to say it. So, first of all, if the set of the 4 points form a convex polygon, okay, what if they do not form? What is the case where they do not form a convex polygon? If it's in one line. If they're all on one line, then you cannot shatter, right? For example, let's label the points alternatively, plus, minus, plus, minus. You cannot shatter it, right? So let's assume this isn't the case. They are not all on one line, and I'm going to take the convex hull of these 4 points. So I can think about 2 cases here. One case is that one of the 4 points is inside the convex polygon formed by the other 3. I think about there's a triangle and the 4th one is inside. What will you do here? Often, let's say it's negative inside and positive outside. You cannot express it with a linear function. The other option is that actually all 4 on the convex polygon. So this number 4 is on a line. And in this case, you'll do the same thing. If you have a triangle and there is a point on one of the sides of the triangle where the triangle was formed by the other 3 points, again, choose the label of this to be different than the other points on the same line, and you cannot choose. So basically, we covered all options, and we showed that no set of 4 points can be shattered. Okay? So you can see that as you move up this hierarchy, and you get more and more expressive, or what seems to you expressive functions, indeed, the size of the set that you need to consider grows up. So this is going to be the complexity parameter that we're going to use. More specifically, we're going to define VC dimension in the same way, right? So we notice that if we have an unbiased hypothesis space, all the functions are there, you can shatter all the instance space, right? I give you an instance space, all possibilities can be shattered because I don't have any constraints on what functions to use. But in general, the larger X is that can be shattered, the more expressive the set of functions, the hypothesis space is, that is less biased. So the VC dimension is going to be defined over this as the largest finite subset of X that is shattered by H. Again, VC dimension is a property of H, a property of a class of functions, and it's going to be defined as the largest subset of my instance space that is shattered by X, by H, sorry. Notice that even if one subset of this size does it, I still count it. Specifically, if there exists a subset of size D that can be shattered, the VC dimension is at least D. If there is no subset of size D that can be shattered, the VC dimension is less than D. Let's go over these examples. This equal here is sometimes confusing. So for half intervals, 0 to A, we showed that the VC dimension is 1. Why? Because we could shatter sets of size 1, but no sets of size 2 we could shatter. Agreed? Intervals, AB. We said that it's 2 because we could shatter sets of size 1, we could shatter sets of size 2. No set of size 3 could be shattered. Right? When you gave me a set of size 3, there are many labelings for a set of size 3, 8 labelings. But one of them was bad, and you just couldn't shatter it. So, and this was true for any set that you gave me. Any set of 3 points, it was just points on the line, I could find a labeling that cannot be shattered. So no subset of size 3 can be shattered. For half spaces, a little bit more complicated. It's 3. We showed that no subset of size sort can be shattered, right? Which means it's less than 4. We did not show that all subsets of size 3 can be shattered, but it doesn't matter. It's sufficient that we have one set of size 3, 3 points in general position that we could shatter, and that was enough. Okay? So this is a subtle issue here that you have to understand. Questions? Okay. So what can we show? Now that we have a definition, in fact, the theorem, the Occam's razor's algorithm, goes essentially to this case. So using VC dimension as the measure of expressiveness, we have the following Occam algorithm. Given a sample of M examples, find some H that is consistent. I'm giving it in the consistent case, exactly the same thing, or analogous theorem with somewhat different constants is going to apply in the agnostic case. But in the consistent case, let's assume that you find H that is consistent with all M examples. if M is larger than this, where, again, forget the numbers here. What's important here is that you're proportional to the VC dimension of H that replaces the size of H. You're inversely proportional to epsilon, and you're inversely proportional to delta. Okay? So if M is this large, then with probability at least 1 minus delta, H has error less than epsilon. Exactly the same theorem that we had before, only now it applies for infinite hypothesis spaces with polynomial size VC dimension. Right? Because we want M to be polynomial. So if M is polynomial, we have Peck learning algorithms. Of course, given that we know how to find the hypothesis, and if we can find the hypothesis efficiently, it's polynomially, it's efficiently Peck learned. Okay, so now a question here. So what's the relation between this? So this is a general theorem. The theorem doesn't say H is infinite. It just says H. What if we go back to the case where H is actually finite? It also has a VC dimension, right? What's the relation here? So specifically, let's say I give you M examples. And I tell you, you know what? My hypothesis class can shatter these M examples. Okay? So the VC dimension is at least M. Okay? M examples, my hypothesis class can shatter it. What do you know about, and it so happens that H is finite. What do you know about the size of H? Okay? Exponential of M. Exactly. A little bit more concretely, what do you mean? At least how many functions are there in H? 2 to the M. Why? It's a Boolean functions. Why are there? So again, M points, H can shatter them. Why is it that there are at least 2 to the M functions in H? So it's a Boolean function, and when I look at these M examples, every example can be labeled positive or negative, and every subset of these M examples I can choose to be positive, and the rest negative. Every subset that I choose to be positive is a different function, right? If I choose these 5 points to be positive and the rest negative, or these 6 to be positive and the rest negative, these are 2 different functions. So this is exactly, and my H can do all these dichotomies. It can express, it can shatter. It means it can express all these dichotomies, so there are at least 2 to the M different functions there. Right? So this gives me the relation between VC dimension, or at least one direction of the relation between VC and the case of the finite. So if I can shatter M examples, I know that the size of H is at least 2 to the M. Okay? You're convinced? That is, if I take log, the log of the size of H, which is the complexity parameter we had before, is at least the VC of H. Okay, so this gives you the relation between these two, and it's a relation that makes sense at least. Okay? Before we had log here, log of size of H, now we have VC of H. Okay, so we have a theory, and now we can go back to our rectangles. So can we Peck learn a set of rectangles? So 2 questions. One is sample complexity. Because it's an infinite class, we need to ask the question, what's the VC dimension? And later on, algorithm, which we already addressed, actually. So what's the VC dimension of the set of rectangles in the plan? Anyone wants to guess? Yeah? 4. Okay. We have a hypothesis for 4. We can take a vote. What? 3. Okay, so before we take a vote, let's look at it. Let's just try examples. So I'm going to start with 4. Here are 4 points. I want to argue that I can shatter 4 instances. Okay, so we're at least in your court. What do I have to do in order to prove to you that the VC dimension is at least 4? I need to consider 16 cases, right? 2 to the 4. The case where this point is positive and the rest are negative, I'm going to put a small rectangle around it. Same thing for here. This is positive, the rest is negative, small rectangles around each point. I cover this. All negative, I'm going to put the rectangle here. All positive, I'm going to put it here. These 2 are positive. I'm going to put a rectangle here. Every 2 I can do. Every 3, I want these 3 to be positive. I'm going to put it here, and so on. So you can see that you can consider all 16 cases, and it's going to work. Now, by the way, can you shatter all sets of 4 points? Give me an example where you cannot. Yeah?
If the top and bottom are positive, and the left and right are negative.
But you need to give me a set of points, because for this configuration, I can actually do what you suggested. For this configuration of points, I can do all 16, I claim. But there is a way to put the points in the space so that it will not work, yeah?
If 3 points are the same length and
Yeah. You can make your life a little bit easier by saying, let's put all 4 on one line, right? And then I'm going to label them alternatively, plus, minus, plus, minus. You cannot do it with a rectangle. Everyone agrees? So, but this shouldn't bother you. The fact that not all sets of 4 points can be shattered, I don't care, as long as there is a set of 4 points that can be shattered, that all 16 labelings are done, I'm happy it's at least 4. Now we have to move to 5. So some cannot. Okay, so in fact, this is the example that you wanted, but it could have been simpler. So we are done with proving that it's at least 4. What about 5? I want to argue that no 5 instances can be shattered. An argument? Yeah?
If you label all the extreme.
Right. So you have first to make a case that this is the general case to look at, but basically this is the idea, right? So there can be at most 4 extreme points, smallest, largest, along each one of the 2 dimensions. Now, it could be that there is some equality, right? Let's assume for a second that there is no equality. So the 5th point is in the middle of this rectangle that was formed by the 4 extremes, and I'm going to change, I'm going to make this guy negative and the other positive, cannot be shattered. If this 5th one is on the side, I can do the same thing, right? It means that I'm going to have 3 points on the side, and I'm going to choose the middle one to be negative and the rest positive. Okay? So actually a simple argument, and we convinced ourselves that the VC dimension is actually equal 4. Now notice that this proves that it's pack-learnable. But in order to prove that I'm pack-learnable, I didn't have to be so exact. I could have made my life easier. What could I have done? Bound. You know, if it's less than 7, it's good enough from the perspective of the bound, right? 7 is a random number here, right? But we could show that it's exactly 5. It's exactly 4. And then we need an algorithm. But we already gave an algorithm, right? We said we're going to find the smallest rectangle that contains the positive example, max and min on the x-axis, max and min of the y-axis of the positive examples, and that gives me something that is consistent with the data. And I'm happy, because I satisfy the consistent version of the Occam's razor. By the way, if you are to run this algorithm in practice, will this be your final hypothesis? What would you do instead? Yeah? You can add a little bit just in case. What does it mean? Where would you go? Yeah, but you don't want to go too much outside. So maybe you will half the distance between this rectangle and the closest negative example, right? So this is going to be an idea of a margin here, right? So, you know, in the future, who knows what's going to happen? And if I half the distance, I increase my chances. I'm still consistent. So everything I could have said about this hypothesis, I could say about your slightly larger rectangle, but I feel that I'm safer, right? Although we didn't prove that you're safer. We need some more theory in order to prove that you're safer. And this theory kind of feels like I need some margin into my theory, right? I need a thick rectangle rather than this kind of zero thickness of the rectangles. And we're going to be able to get there, actually. But at least now, you intuitively, you know that, well, I have a theorem, I have guarantees, and also in practice, I'm going to do something slightly different that will do better. Okay, so we are done with proving things about learning. We have a theory. I want to say something about what else can the theory do. So one thing that the theory do, it can give you also lower bounds. It's not only that if you take these many examples, you're guaranteed that the future is going to be good. Actually, sometimes you have to take these many examples. Now, it's a lower bound, which means it deals with the bad situation. Basically, it means essentially that there is a distribution, right? So consider this concept class. And I have some VC dimension that is non-trivial. We need this for the theorem. Any learner, any epsilon and delta, to prove a lower bound, I need to say, well, there is some bad distribution, and there is some function in this class C such that if you don't take enough examples, it's not going to be good. That's what it means to be a lower bound. So you may not care about it because it's unlikely that this is the distribution that you'll incur in nature and that this is really the bad function that you care about. But it's important from a theoretical perspective to understand that these exist. If one exists, probably there are many that exist. So we can prove, or one can prove, a lower bound. And the interesting thing is that it depends on basically the same thing. So the gap isn't that significant between the lower bound and the upper bound that we showed. It also is proportional to VC, inversely proportional to epsilon, inversely proportional to delta, and so on. So the lower bound is really the same as the upper bound modulo constant factors and the 1 over epsilon factor that we had. Before we had epsilon squared. So again, this is of theoretical significance. It says two things. One is that it's possible to have a lower bound. So there are some bad cases, hard cases in learning. And two, it probably also says that the upper bound that we proved is not tight enough, right? So probably in realistic situation, you will not need that many examples. But, and you know, what I showed here also is not the tightest bound that people can prove. It's the simplest bound that people can prove. Okay, so that's one thing. So let's conclude here. So what do we know? We have a framework that provides a pretty good model for theoretically analyzing the effectiveness of learning algorithms. We talked about sample complexity, and we said that the sample complexity for any consistent learning using the size of H or the VC dimension of H is related to learnability, or it dictates learnability. In the case sample complexity is tractable, we need to look at computational complexity of finding a consistent hypothesis, or, as we relax it later, a good enough hypothesis in the agnostic case. And, I already said that, there are not tight bounds, but they are still enough to separate learnability from non-learnability, right? For interesting classes, like, as I said, finite state automata, we can prove that they are not learnable in this learning protocol. In fact, one can prove that there are other learning protocols in which you can learn finite state automata, but not this learning protocol where you observe examples with labels. And also, the theory allowed us to develop some understanding of representations. In some cases, you can learn using this representation, but you cannot learn using other representations. The same data. You have to be careful which representation to use. Okay, so there's a lot more things that people can say, and I'm not going to say. So you can extend this model to deal with noisy data. You can extend this model or make it more restricted to deal with specific distributions. You can extend it to deal with probabilistic representations, neural networks, finite automata. You can talk about active learning from this perspective. You can talk about teaching. We mentioned teaching at the beginning of a few lectures ago, and also study it from this theoretical perspective. Prove that some class of functions are teachable and some are not teachable. There are some very interesting extensions. For example, one extension that is important is what is called today the Peck-Bayesian theory. So we had one key assumption, which is this distribution free, right? You can impose another assumption where the learner has some priors on which hypothesis they like more and which hypothesis they don't like. So some prior distribution over the space H, and this gives you a tighter theory on what can be learned and what cannot be learned, and better bounds. This is called Peck-Bayesian theory. Now, the cool thing about this theory, beyond the ability to model learning in a concrete way. So if you think about the situation in machine learning, there was machine learning even in the 70s and early 80s. But essentially, if you look at papers from that time, they did not have an understanding of why things work, when things work. It was just a completely experimental field. Not that today it's not an experimental field, but today there is a lot more understanding of why things work, when things work, understanding of different components that dictate learning. And in particular, it allows us to understand better model selection. Which model selection means which hypothesis class should we use when we want to learn something. And specifically, it allowed us to develop algorithms that were really driven by questions in learning theory. So I talked about WINOW already. WINOW was a solution to a question that came from learning theory. The question was, in theory, there is an algorithm that has these mistake bounds, k log n, for example. Is there a practical algorithm that can accomplish that? And we show that there is. Support vector machines, as we'll see in a week or so, can be understood directly from result in learning theory. You want to choose the linear separator, but you want to choose among all linear separators one specific one under results that are guided by learning theory. And boosting, exactly the same thing. So it's a very important algorithm today. And it all started with a learning theory question. We can prove, we have a notion of Peck learnability. We can relax or try to relax the notion of Peck learnability and say, instead of epsilon, a small epsilon, I can say, let's assume that I can learn with epsilon that is bounded away from a half. So I know that I can always learn, I can be pack learning, if your epsilon is like a half minus something small. Does that mean that I'm pack learnable? Again, you give me an algorithm that we call weakly pack learnable, in the sense that you can always learn if your epsilon is 0.49. Does it mean that you can use this algorithm and develop an algorithm that is going to be as accurate as you want with very, very small epsilon? It turns out that the answer is yes, and this gave the boosting algorithm. So a lot of practical things came out from asking a theoretical question. Now, the next few slides, I'm not going to do it now, but I'm going to do it before we get to SVM, because in SVM, there is a very interesting notion of VC dimension that drives the theory, what I call data-dependent VC dimension. We're going to talk about it in a couple of weeks. The next two lectures are going to be devoted to neural networks, and then we're going to jump back to boosting and to SVMs. Questions? No questions. Okay, so.
About the neural network, are we going to talk about the basics, or are we going to talk
We're going to have